Hello guys, so today I have participated in this BirdClef 2025 contest, uh, and it's been like in 2024 they did this contest, and I mean this contest has been going on for a while. Like every year they get this audio data set of um, birds, uh, frogs, amphibians, reptiles, all this, and we just have to classify. Now, here the thing is, there are various classes around like 200, like above 150, you can imagine. So, yeah, couple of challenges like since the classes are pretty huge and these are audio data set. So, yeah, so let's try and participate in this contest. So, I have opened a notebook here. Let's call it BirdClef 2025. And I'm doing this for YouTube, so let's say YouTube, and let's name it EDA. Cool. So hopefully I will be able to train a model and do some EDA in this video. Let's do this and this. And this is not opening. Cool. Ah, okay. Let's start off with some import. I don't need to. Now they haven't given a couple of information about their data set, so I mean, there's a lot of information, but I guess the only thing we should be caring about is this train audios and the train CSV. This contains the labels for the audios, and these are the audio files. Train soundscapes and something like which are unlabeled data. I don't know why they have given it, and they are assuming that we will build a model then pseudo label it. I don't know whether that will fit anything good or not. But yeah, we got some secondary labels also. So these are something like they are very less confident. Like we have a audio signal and uh, whiteboard. Yeah, we have an audio signal. So there is a primary label they have given us, and that basically means that that animal's voice is predominant in the video, whereas there are some other sounds also involved, and those sounds they are labeling as secondary labels. But yeah, we will just keep it simple and we will stick to primary label. So let's start with some import. And by default, we will be importing pandas, we will be importing numpy. Cool. Then since we are dealing with audio signals, we will be importing Librosa. It's a pretty cool library for dealing with audio signals. So it has some couple of functions which we can use for feature extraction. Uh, Glob, get the datasets, dataset path. Then let's import torch. Let's import torch nn as nn. Then OS random. Now what else? What else? Oh yeah, matplotlib. Matplotlib dot import pyplot as plt. Now I don't need that annoying warnings. Yo. Filter warnings. Ignore. Okay. Let's first import this, then we will import on the fly. Cool. I should also import Seaborn. Let's zoom down a bit. What else? Okay, cool. Yeah, by default, I need SMS. Okay, now let's define our config class. Okay, now here we will be doing, we're just saving the path. Train audio goes here. Then I need one seed parameter. Then main CSV, same base path. Then let's look at sample summation. Then I need 10 soundscape. I don't know whether I will be able to pull inference in this one video. But yeah, let's see. Fingers crossed. Yeah. Then yeah, they have told like so all the recordings have been done for at a sampling rate of 32 kilohertz. And they have told like this 32 kilohertz, they have done it only where it is applicable. So it may happen a couple of signals are not in 32 kilohertz. So yeah, we will find a way to deal with those. So let's save this. So I need 32,000. So that's my sampling rate. Then there are classes. This we will be needing. Uh, can I know how many classes are there? There are around 206 classes. So not around, there are exactly 206 classes. So this is yeah. Let's stick to our config. Now let's create some helper function. Now the major helper function will be setting the seed. Now seed in config seed. I don't want to return anything. Cool. Then first of all, random.seed seed np. This is for reproducibility. Random.seed. Then since I'm using torch, so all the weight initialization, I want them to be reproducible. So I will put torch manual seed. Then there are, so for Q, if I'm doing GPU training, which I think I will be doing, so then also we have to do some CUDA side manually seeding. So if CUDA is available, then I will be doing torch CUDA, same thing. The first one is for CPU, this one is for CPU, and this one is for GPUs. And another thing is manual. These are like just default steps. Cool. Now other seedings involve torch backend, deterministic, yep, then torch backend, um, some benchmark if I remember. This we want false. Now in the end, once we are all done, let's print a cute message. All set done. Set seed. Cool. I am recording, right? Cool. Yeah, so this should set our seed. Done. So we are done with seeding. Now let's load our dataset. Let's create a couple of lines here. Okay, cool. Now let's load the train CSV PD. Let's look at sample 10 rows. Oh, okay. No such directory. Oh, okay. Sorry. Okay, cool. So we have, so this is how our data set looks. So the primary label is the one which is a label for which is the dominant class in the audio. Then we have some secondary labels. We can see there are some other classes present in the audio, but they are very less confident over it. Then we have a rating for the audios. So these are the ratings, and they have told like that's vary between 1 to 5, 1 being the low quality and 5 being high quality. And there are some zeros, which means they don't know how to rate. So yeah, we have zeros here. Nice. Okay, cool. Then what else we need? So since this is CSV, this list will be stringified. So I'll be needing this part if I'm gonna use them. Otherwise, yeah, let's just do this. So since the list, I have to convert the stringified list. So let's import literal eval. Now, so I have to do for two of them. Copy this. Secondary labels. Now, what I have to do is I basically have to uh, convert it to a string, convert it to a proper list. Then let's join them. Apply x. Let's add some delimiters here. Join literal eval of x. This will join this thing. Now, yeah, cool. So this should do it. Now, these are the file names. Here I just have to add a prefix to it so that I can use this file name while loading my audio files. So let's put df. Now these are my train audios. So here I have to put just the train audio base path. Cool. So name. So here I have to do config train dr x. Cool. Now we should be looking at a proper data set. Okay, cool. I hope I didn't make any mistake. This basically means there were empty list. Yeah. Okay, cool. Let's load it again. I'm just pretty curious whether yeah. Okay. I got one class. Cool. So yeah, this is done. Now, the basic pipeline while dealing with audio files is like we convert the audio to spectrograms, and spectrogram acts as our image for a model, and then we use those images uh, for training our models. So we will be doing something like that only. So just before that, let's do some quick analysis. So first of all, let's perform some null checks. Data df. Okay. Uh, Cool. We do not have any null values in primary label, but we have some null values in latitude and longitude, which I don't think I need. Cool. Then let's check the distribution of the ratings. So let's call it distribution of the ratings. So since I have a big monitor, I can put a big size here. Let's call it 15 to 3. None. I want a his plot of data df and of the column rating. Good. Then let's look at, since they vary between 1 to 5, so let's put it here. So I need 5.5 so that my 5 will be also counted, and let's jump 0.5 distance. Okay, we have so many files in 0 rating. I don't know how to rate them. Okay, cool. Uh, we have, okay, we have some kind of a bimodal thing. We have zeros here, we have 4 to 5 rating here. So we are good in one case. Okay. Now, let's check out the distributions of the primary label. Distribution of the primary label. Cool. So same thing I'll be using. And instead of rating, I'll be doing primary label. Now they will be so much. Oh, sorry, they will be too much. So I'll be rotating them. Because we have 206 classes, so yeah. Bada boom, bada boom. Cool. So this is how our classes look. I think there's a better way to do it. Okay, these are pretty clumsy. Okay. Somehow this is decent. So we have some skewness in the data set. Okay, cool. Now, let's look at the distributions of each rating. I'm pretty curious, like how many are in 0. So I can see this, but let's see if it's, it can happen like one class is particularly 0 rated. So let's check that. Okay, so what I will be doing, so I will be with ratings. So I have 4 and all this now. So 4, 6. Okay, let's plot a little bigger. This I don't need. Then here I'll be applying filtering. Okay, we have filtered this and this. Now let's put a title. Uh, Rating R. Grekis. Okay. Okay. We have so many classes with 0 rated. Okay. 0 rated are pretty clumsy, I could say, because there are so many classes, but there are only few classes which are Okay, I'm wrong. Okay, there is one class which is around 500. There are around 500 audio files of them, and yeah, they are zero rated. Okay, this is troublesome. Uh, Maybe zero rating because they don't know how to rate it. So it can be good, it can be bad. So don't know. Okay, cool. So now let's check out. Yeah, for that. So we have audio signals, right? So before dealing with audio signal, we should be able to get some stats out of their length. So I mean the duration of the audio signal, because the spectrograms that we will be building for a particular interval, or for a particular length. It can be 5 seconds, 10 seconds. And in order to do that, we first need to figure out, like, in my train audio files, how the length is varying, like from which range to which range the audio durations are. So in order to get that, we will be doing some quick stats. Okay, let's check the statistics. It's of audio duration. Okay, now let's sample 100 audio signals. So for IDX, throw in a sample for 100, and yeah. Now we have the file path saved already, right? So I'll basically use that and put it in Librosa and get the audio data. So SR, I don't need the sampling rate. So Librosa returns two things. It's the actual audio data and the sampling rate. So let's load file name. Yeah, this will get the path. Then we have to tell Librosa which sampling rate to use. So we know all of them are sampled at 32 kilohertz. So we have also saved it in our config. So yeah, start. Now this will give me the data. Now I need to put that get the duration. Librosa get duration. Now it takes the signal and the sampling rate. So which is config SR. Cool. Now once I have that, let's build the distribution. So let's call it a dimension of 10 to 5. Then let's call it distribution of, fuck. Okay, distribution of audio lengths. Okay, cool. Then let's plot this. Oh, I can do SNS, right? Let's plot. Now here I have to get this durations. Actually, I think I can give this durations. Then let's speed distro. Actually, I can use describe here also. So let's create a data frame then. DDF. So for duration DF. So columns, let's call it durations. Then data will be list of my durations. Now I can use this with this and call it this, and I can also get the describe. Run. Okay, it's taking some time to read the audio files. Okay, so what we will be doing is, okay, one column passed, add 100 columns. It doesn't take that. Okay, so we have some audio signals. Oh, okay. So we have a minimum length of 2 seconds and a maximum length of 552 seconds. Okay, cool. So many audio files. Let's increase the bin. Oh, actually, let's move this here. I don't want to rerun you. So let's rerun it here and increase the bins. Let's put it 100 bins. Okay. Okay, cool. This kind of an outlier. I think if I sample more, I will get more clarity over the distribution. But yeah, so we have 2 seconds audio files, and we have a massive of 500-second audio files, which is more than a minute. So we will be, so if we want to process the audio files, we have to fixate it an audio length. It can be 10 seconds or 5 seconds. And we have to stack out all the audio files with the 2 seconds. So yeah, here's what we will do. So we got the audio. It will look something like this. Okay, now this is our audio signal. What we will do is we will collect the spectrogram out of it. Okay, now this will help us to figure out the frequencies captured in the audio. But the issue with spectrogram is they kind of show us the averaged frequency, so we cannot distinguish the frequencies in the audio signal. So all the frequencies are mixed up in those spectrograms. So in order to avoid that, we will convert to Mel spectrogram. Okay. Okay. So it's a combination of short time Fourier transform and the Mel scale. So it just puts on more filter, and for a particular time zone we can see the different frequencies, so in during that time. And why Mel, why not a normal like SFT kind of a transformation? It's because Mel is so we call it melody, and it's a scale which like symbolizes how a human perceives the audio. Now what does that mean? Like we all know, like we humans have a range of frequency that we can hear, right? So it's like 20 hertz to 20 kilohertz. Yeah, that's the one. Yeah, so we can hear around this band only. So anything above 20 kilohertz, we cannot listen that. Now the Mel scale basically helps to understand our perceiveness. So it's a logarithmic chart. And what does this, okay, let's open it in a new image. Zoom. Cool. So what will happen is if we hear a audio at this frequency and we hear a audio at this frequency, okay, we will be able to distinguish them. Okay, but if we hear a audio around this frequency and we hear a audio around this frequency, so you can see the distance between these 2 points are minimal, so the distinguishing, so we cannot properly distinguish them. So I don't know whether I can do this. Oh, I can do this. Cool. Why is it saying uploading? Okay, so if we hear two audios at, let's say, this to this, okay, now you can see their differences. Let's call it D1. Okay, now let's say we hear a audio around this frequency. It's a high frequency audio. Again, let's do 2 units frequency difference. Now here we will observe like the difference is minimum, like not minimum, is very less as compared to, yeah, our D1. So here maybe there is a spacing issue, but I hope you get the point. Yeah, so D1 will be more than D2. So it's easier to distinguish lower frequency than to distinguish higher frequency. Now this is something we human have. So frequencies close to 22,000 are lesser distinguishable, but frequency like around 10,000 or 12,000 we can clearly distinguish them. Now since we are building a model, we want to replicate this behavior inside the model. So in order to do that, we will be using Mel spectrograms instead of normal spectrograms, because these spectrograms will reflect how the human perceives the audio. Okay, let's put it side. Bada boom, bada boom. Okay, so let's actually visualize the audio. So let's check out spectrograms. Now before we do that, uh, 4 things we need to plot. One is the normal audio, okay, the normal audio signal, the spectrogram signal, then a amplitude signal. So we will be converting the spectrogram into a decibel scale. Then we will showing a Mel spectrogram. Okay, and there we can distinguish the patterns in the frequencies. So yeah, so uh, let's create a function. Let's call it signal, and what it will take? It will take a file path. Okay, now this should return me 4 things. So let's call it subplots. And I need 2 plus 2. Okay, then pick size, let's make it 2010. Okay, cool. Now from the file path I will be collecting the class. Okay, now this is, let's look at the file path. So here we have this, and then let's look at a file path first. I can simply open this. Yeah, so here we have audio signals. Okay, copy. Now this is the class, and this is the collector's name, like which community collected this audio file for this class. Yeah, so let's put collector also, and let's split the file path by slashes, and let's take the last two elements. Okay, now this will be my class and my collector. Then I'll be reading the audio signal. Libro load file path config sr. Okay, now this will give me the signal. Then I have to build a grid. So so this is there. So a grid of 2 cross 2. Then let's put a title over the grid. So if I remember something, title. Okay, yeah. Some kind of a super title. So yeah, let's make subtitle. Let's call class as class, and let's put the collector name as collector, and let's give a font size of 16. Okay, now let's plot the raw signal, and to check my function on the fly, uh, I'll just randomly take any audio signal so that I can check it. So 0. Okay, now here, now Librosa has plotting function, so that I can directly use. Web show, then it takes YSR, and it takes, what's the size, remember, oh yeah, it takes which axis I want to use. So I'll be using 0 0. Then let's put a title over this. So let's call it raw signal. Okay, and show. Okay, cool, we got the raw signal here. Okay, now in the second part we will be showing a Fourier transform. So let's call it Fourier transform. Transform signal. Okay, now to convert it into Fourier transform, so we will be using STFT. So what does STFT does is, so if you guys are not familiar with Fourier transform, I highly recommend you to watch 3 blue 1 brown's Fourier transform video. That's pretty intuitive, and yeah, I will also link it in my description. Yeah, this is pretty intuitive about Fourier transform and how does it work, how you can decompose a signal into sines and cosines. So yeah, this is pretty intuitive, so you guys should watch it. So what we will be doing it here is, so we will be applying STFTs. Now how STFT works is, so in Fourier transform we completely transform this audio signal to a spectrogram. Okay, like this. But in STFT we chunk the signal and we do it in a sliding window form. So let's say I have this kind of signal. I will put a window, and in that window I will compute the spectrogram. Okay, then I will move this window. Okay, and there can be overlapping, so that's also a parameter we can give. Then I will again plot the spectrogram. Okay, now how this will help me is, so this is time, and here I'm like converting it to frequencies. So at every time I will see the frequency differences. Now this is how STFT is kind of better than a complete Fourier transform, because we will decompose the signal into different intervals and get out the different frequencies that are like what making that audio signals. So yeah, uh, so Librosa has a function so we can use. Let's check that out. STFT Librosa. Yeah. So we have to call like how many FFTs we want to do. Hop length is basically the strides. Like if you are at here, how much you want to jump. So that's the hop length. Then window length is pretty standard. Then you have a window function, which window function you want to apply. So all this. So we will stick to like standard. Only this number of FFTs and hop length we will modify. So let's call it this NFFT. So let's store it in our config. Now here we'll be needing a couple of parameters then. So and then number of FFTs, let's call it 1024. Okay, there they have used 2048. Let's stick to 1024. Then hop length, let's make it 500. Then now this is for STFT. Now when we will be doing Mel spectrograms, there are a couple of parameters which we need to give. So first one will be like number of Mel bands we want to do. So this is something kind of hyperparameter. So people play with this parameter for getting different features from the audio signal in Mel spectrograms. So I will keep it high, 128. You guys can try like 32, 64, doesn't matter. Then frequency, like the minimum frequency we want to look in the signal. So it's like to convert a normal spectrogram into a Mel spectrogram, there are a couple of steps we have to do. It's like first, ayyo, ah, yeah. So first of all, to get a Mel frequency, okay. So we have a constant here, then we put we convert into a log formula. So I don't exactly remember. I think this was some 700 thing. Okay. Mel spectrogram conversion formula. Ha, no one is giving. I think this guy must have given. Okay, okay. Yeah, you can see like it's the raw signal. Then we are converting into a frequency domain. You can see. Then it's a short time Fourier transform is doing. Then it is converting to a spectrogram. So we have this signal. So we put a sliding window kind of algorithm. Now in each window we compute the Fourier transform. Then we keep on applying and we finally bring a spectrogram. Yeah, this will look something like this. Now we have a male scale. So I just need the formula. Yeah. Okay. But essentially what we are saying here is like as time is progressing, so we have frequency bands, right? Now in each frequency band, how are they like arising? So a frequency with a value of 64, okay, how is it varying with time. Okay, so these are bands, and this is how we process audio signals. And we just give this spectrograms to the model. We apply a CNN kind of like a computer vision. So from an audio problem, we convert it to a image classification kind of a task. So yeah, now the middleware being the spectrograms here. So I'm not getting the formula here, but should be somewhere. At least one guy should write that. Okay. Mel frequency. Oh yeah, this is the formula. Oh, so I was right. I think, yeah. So this I'm not sure. I remember it was some 2000, or maybe it's a different log base here. Okay, cool. But this is how you convert a frequency value to a Mel frequency value. So yeah, coming back to, so first of all, when we have a spectrogram, we declare some frequency range. We call that F mean and F max. Okay. Now within that frequency range, we basically uh, see it like something like this. So I have this band here and this band here. Okay. Now within this frequencies, like within this frequency band, how many Mel filters I want? That's your N mils. Now how does that work is like, when I'm saying 128, it put this domain, and now within this domain it puts points, and it puts around 128 points, all equally spaced. So something like this. Okay, so all 128 uh, points are placed within this range. Now these are like, again, more frequencies here, right? F3, F128. So yeah, now we are producing more bands of frequency in here. Now there is some mathematics involved here, and once we have this many number of Mel bands, we put some calculation there, and it basically convert this Mel bands into some triangular filters, and then it produces a Mel spectrogram. So to keep it concise and simple, Mel spectrogram, librosa dot feature Mel spectrogram, simply. If you guys are interested in learning the math, can YouTube that. But yeah, the idea is something like this only. And we don't need to do this. We just need to provide the parameters. It will automatically give us that. So yeah. So yeah. So I'll be using 128 now. For frequency band, I can put some 50, and let's put 16,000. These are some kind of a default values, and we need power. Then another thing we will be needing is hop length. Hop length, okay, I have already given. Cool. This is there. Okay, cool. Now we will apply STFT. Now I can say config and NFT, then hop length. Now let's not consider the negative values. Let's just look at the signal, how it is. Okay, then I need to show this. Now if I remember, we have some spec show. Yeah, you get the data, you get the hop length, and you get that. Okay, now let's it. Librosa display spec show. Okay, FT SR. Now, yeah, x-axis. So this takes time, and y-axis we'll be using linear. Okay, and x will be axis. So we want it in here. So we'll be using 0 and 1. Now once I have this, let's put a color bar over there, and let's call it I think this also takes. We put a color bar. I think you just get the okay, yeah, here okay. I think you just get the X. Then access 01 subtitle. So this is our spectrogram. Cool. Let's look at this. Didn't show up. Okay, what went wrong? Got the signal here and here. It didn't give me an error, which is good. Okay, and F50 this. You didn't show up, and something wrong. I'm calling this correct, right? Okay. I give you this. I get this title. Yeah. As for power signal, right? Yeah. Time, sampling rate. I have given sampling rate. Why you are not showing up? Okay. It's not appearing. Why? We'll call it. Okay, now we should be able to see the Fourier transform signal. Then we will convert it to a log scaled. So yeah, we cannot see anything here. Okay, there are some frequencies here, like in this band. Okay, we can see some. Okay, but these are pretty low. So in order to show them, we will convert it to a log scale. Okay. Fourier log scaled. Fourier transform signal. Okay. So we'll be converting it to decibel scale first. Librosa amplitude to dB. So we'll be converting to decibels. Then let's put max Now what this does is like you have the signal, it converts into decibel scale, so all the amplitudes will be converted to that. And this reference is a formula. We can set it to 1. So it's just a formula parameter. So if I show you, okay, so the computer is some form of this. Okay, now like the more we increase the signal, the lesser so we will get. Okay, but it's also uh, better to use the max one. Okay, so that we will get a normalized form. Okay, so yeah, I will just stick to np max. Okay, so np max is like the global maximum, so it will uh, so irrespective of what signal values we have, it will just normalize that. Okay, cool. Then spec show. So now I will be giving FTDB sampling rate, time, and in y-axis this will be log scaled. So I will be giving log, and x will be 1 comma 0. Okay, then big color bar, same as second, and I need for 1 0. Okay, now I need to give a title, so access 1 0 title spectrum. Now we should be able to see some frequencies. Okay, cool. Now the same signal is converted into decibel scale. Okay, and now we can visualize the frequencies. So here we were not able to visualize it. Okay, okay, yeah. Here if you see, now once we have converted into log scale, it's pretty easy to visualize them. Okay, now this is that. Now let's convert it into Mel spectrogram. Plotting Mel spectrograms. Okay, so a couple of parameter it needs. So I'll just search that also. Okay, okay. So f mean same as what we have given in config. F max, F max. Then power will be config dot power. Then number of mel bands will be 128. Okay. Now, cool. Now this one also let's convert it into power into decibel scale. Prosa power to dB LSP and same thing. Okay, cool. Now here also we will be needing the color bar. So Prosa display spec show. Y-axis will be my mel scale now. Okay, config sr, and I think I can directly use that. I don't need to repeat this. Okay, this max. Okay, it's really 1 1, and I'll just copy these 2 lines. Now we'll be calling it Mel Spectrogram. Okay, taking some time. Cool. So the log scale spectrogram and here the male scale spectrogram. So both are kind of similar, but we can see like uh, the frequency values here and here. So we have some kind of more fine tuning here, we can say. Okay, more discretization is happening here. I guess if we plot for more signal, then it will be able to make, then we can see. So let's call it for row in data df sample iter rows, and then give this show signals. So row, yeah, this one is more grainy and this one is like more smoothen. This is essentially like we are doing a normal log transformation here, but we are doing a male scale log transformation here. So both are similar, but this is more understandable to the model than the signal. Yeah, and we want the model to learn this because this is something how human perceive it. So yeah, here we are seeing like different bands of frequencies here. So like from here to here. Okay. Why my F max? Okay, cool. Look pretty cool. Yeah. Whoa. Eren Yeager. Okay. Okay, cool. Now, we got our audio signals, so we somehow visualize them. Now we have to apply this same spectrogram conversion while we are creating data sets. Okay. Now, in order to do that, we'll be writing a preprocess function that will take the audio path, read it, convert it into a spectrogram of a particular dimension. Okay, and that we will be feeding into the model for training. Okay, now before we do that, let's quickly build our dataset classes and model classes for training. So dataset. Okay, let's call it BirdClef dataset, and it uses torch. Um, I don't remember utils. Torch dataset. Torch utils dot data. Okay, then it takes a data frame. Okay, then we'll be setting a mode. Okay, Okay. And self mode. Now this will help us to use the same dataset class while we are uh, doing testing of our images. Like we are building dataset for our test dataset. So yeah, this mode will help us in that. Okay. Then we need to implement the len function. This will be used by the data loader classes. So we'll be returning len of self df. Okay. Then we need to implement the get item method. So it takes an index and it does row. So self df lock idx all the columns, then file name and label. Okay, first let's collect the file name. We will collect this, then we will be converting it to a spectrogram. So let's write that here. Okay, now let's check if self mode equal to train. So we have to output the label also. So and also we have the labels, but we want to encode those values, right? So let's encode them then. So let's call a label mapper. Okay, so we got label index. Now what we will do is for ex label in enumerate of let's sort the classes, then we will use data df all the primary labels, but we will collect them uniquely. So all the unique classes that we have shorted them, then we have assigned this label like this. Okay, now same thing. Now this will give me string to number. Okay, now I need a reverse mapper that can give me the reverse of it. So I will be writing label for label idx in label mapper items. Okay, now this will give me a class index which will be integer. Now this is to like from the integer to the class name again. Okay, now this is something we will be using during inference if we can do that. Okay, cool. So this, then we will be using our label mapper. Then I'll be writing primary label returning x and y, and if it is not not in training mode, then we will be returning only x. Now let's define our x. Now x will be something let's call process thing, then let's give the file name. Now let's implement our process thing. Okay, now the train audios are in varying length, so we need to stay fixated over a fixed length. So let's stick to 5 seconds. Okay, now in those 5 seconds we will be collecting all the data and we will be converting into spectrograms. So let's call it process, and it takes a audio file, audio file, audio path, that's it. Okay, same, we will be reading it. And same, think here. Now, a good strategy is to like uh, get those value, like multiply this value to a very high value, so that if we have very shorter signals, because in the end Mel puts a logarithm over that, so we will never overshoot the values, okay, or like saturate. So since we have a saturation there, we can multiply the signal with a higher value, so that low amplitude signals will get chance to get recognized. So for example, this here, so I have a signal like this, okay, which is varying between like 0.15 to 0. Like 0.20 to 0 negative of 0.20. Now I have this signal, okay, so which is loud, like which has more amplitude than this signal, okay. Now this type of signal, it's better to multiply them, like basically scale them, okay, so that we can perform the same processing and those values will not get nullified during pre-processing or model training, so that model will recognize those signals. So so let's scale it. Let's call it this, okay. Then let's decide on our duration, okay. Let's pick a chunk duration, so we can select 5 second, or let's give 10 seconds, okay. Now whatever length of my audio signal is, okay, I need to get a 10-second signal, okay. Now within that 10-second signal, how many data points I will be looking at? So that's my chunk duration times my sampling rate. Cool. Now this many data points I need to have in the audio signal, okay. Now first case, if the audio signal is less than my mean length, okay, then what I can do is I can stack the same audio signals. So for example, I need to get 10-second signal, okay. Now I have an audio signal which is of only 2 seconds, okay. I will basically stitch the same signal again and again until it is hitting the 10 seconds signal. So that is there, okay. So if len of data, if it is less than my mean length, then I'll transfer my data to, I'll basically stack them, tile. So how many times I have to stack them? So it's called count, and let's count will be my seal of, so I need to divide my minimum length upon the length of the data I have, okay. uh, let's make it int, okay. So if I need 10 seconds, okay, so how many times I have to repeat this? So that's basically 10 second upon this 2 seconds, right? So 5 times I have to repeat it. So this is this calculation. Seal for, if even if I am exceeding the signal, that is good for me, because later on I can put a truncation over that. So yeah, cool. Now since they have told this, like uh, not all signals are captured at a sampling rate of 32K, okay. So we need to bring all of them to that, so that we can apply this minimum length, okay. So basically if I need a minimum length signal and my audio signal, so basically if I need a 10-second signal and my audio signal is of, let's say, 171 length, okay. So I'm only interested in the 170 data points that I have, okay. This one I can overlook, okay. So now the idea for this truncation will be, so many ways we can truncate. We can truncate from the back, we can truncate from the front, but it's better to truncate from both sides, because in every audio signal there will be some pause moment, okay, when they are recording, okay, and when the recording is finished there will be again some pause moment. So it's better to truncate them from both ends, okay. So it's basically kind of a cropping only, but yeah, okay. So let's call it making the data length divisible by my min length, okay. Now when we will do it, so let's call it leftover, so len of data min length, okay. Now if my leftover is more than 0, if I have some leftovers just like this 171, okay, so I will remove 0.5 from here and 0.5 from here, okay, so that I will get the 170 signal, and which is like divisible divisible by my fixated length, okay. So if that is there, so let's calculate how much we have to crop from the front. So that's basically leftover upon 2. Now that's like 0 to leftover upon 2. I need that. Now from the back I need to crop leftover minus front crop, okay. So 0 to 0.5, that's your front crop, and back is basically your, so this is your whole distance, right, okay. So I need this portion, okay. So leftover minus front crop, okay, cool. Then data, so we'll be slicing it, front crop to my len of data minus back crop, cool. So we got the signal, and if the signal is lesser than my desired length, then I'm stacking it up. Now, if my length of the data is not a divisible of my desired length, then I'm just cropping it from both ends until it is divisible. Okay, cool. Now I will simply take the I will take the data up to my fixated length. Okay, so truncating the signal to min length. So data, and I need to take only up to my min length. So it's like I have the signal, okay. If I am only interested in 10-second window, okay, and let's say this is around 555, okay. So we started with cropping this, okay. Then after that I can randomly pick any 10-second window from this part, okay. Now just to keep things simple, I'm just picking from this to this, the 10-second signal, okay. Now yeah, here min length basically tells like the number of data points I have to take, okay. Since we are dealing with audio signals, so every time I'm saying like uh, this 10 seconds is basically means 10 seconds time the sampling frequency, that many number of data points I'm capturing, okay. So this is like seconds I'm talking, but the number of data points we will be capturing is basically 10 seconds time my sampling rate. Cool. So once I get the signal, now I will create a Mel spectrogram. Okay. Creating Mel spectrogram. SP. feature Mel Spectrogram. Okay, so same as how we did in the plotting function. So I'll be giving all this parameter fmean max, okay, power. So all this parameter will make sense if you guys are aware of the concept of Mel spectrogram. If you guys are not aware of it, so basically just go over YouTube and search any video. So there are plenty of videos available. So how what are Mel spectrograms and why do we use it? Config F50, and one more thing, I think we left hop length. Is it recording? Yeah, it's recording. Okay, so config hop length. Okay, now we got the Mel spectrogram. Let's convert it into power scale. So librosa power to dB, then Mel sp, and we can put a ref of 1. Okay, now after this we got the spectrogram. Now as per, since we will be training neural networks, so we need to normalize it. So normalizing the feature values. Okay, so let's provide epsilon. So let's make it this, because I'll be using min max scalar. It can happen like your max and the mean, so maybe the signal is empty, so nothing happened. So in order to avoid those cases, because we will get some zero division errors, so I'll be assigning this epsilon. Now Mel sp, so all the values subtracted with my Mel sp mean upon then Mel sp max. These are all numpy arrays, so we have this mean and max methods. Okay, plus epsilon. Okay, cool. Now this function will produce a signal dimension of so let's try this function first, then you guys will have more clarity. So let's give this. Okay, we have this. Let's give our data df, and training mode will be by default. Then if I call process with data df of let's call it file name sp, file name values 0. Okay, now this will give me a Mel spectrogram. Okay, but I have to somehow use it in the, like I have to crop out some values so that I will stick to one fixated dimension for the image. Okay, so let's first print Mel sp shape. Okay, now this will give me the channel's width and the channel's height and width in those dimension. So in order to show this, I need to convert it into first let's look at the dimension. Okay, I got some error. Okay, front crop. Okay, front tab has no shape because I'm not returning it. Yeah. We got this dimension. Okay, now this is a 2D image. It doesn't have any channels. Okay, so 128, these are like the frequency, the Mel bands, that's the dimension 128. Now 641 means like in each band I'm getting some features there. Okay, and I'm getting around 641 feature. Now, just to stick to a proper image shape, I will truncate it into 640, let's say, because that's a multiple of 10. Okay, so Mel SP. Okay, then I'll be doing this. So far it's not yet three-dimensional, I guess. Oh yeah. Okay. I think somewhere I missed it. I have to convert it into three-dimensional. Yeah. So let's assign a dimension and get this. Okay. So this will just pop up a new dimension to our data. Then we will give it to the Mel spectrogram. So Mel spectrogram is it can take dynamic inputs. So even if we are giving a 1D signal or a 2D signal, it will still give us a Mel spectrogram. Okay. So here we are converting into a three-dimensional figure. Okay. Then here we are converting into a 2D figure. Mel spectrogram will produce a 3D figure. Okay. And from that we will be cropping out 640, like the initial 640 values for each band. Okay. Now if I look at the figure, so this will look something like this. Okay. So one here being the channel. Okay, which got produced because of this. Okay. Then 120 is the number of bands that I have, and 640 means in each band we have a couple of features there. Okay, like the time features that we have. Okay, now I'm just truncating the first 640 values. Okay, so that all my spectrograms will have the same dimension. Now if I plot it, so it will look something like this. So this is okay. First we have to transform to ch transform from. So right now it is in channel height width, and to plot it in pie plot, we need to convert it into h, w, and c. Okay, so plt I'm sure Mel sp. I need to reshape it. Okay, I need 120. I need 640 here, and rest over whatever values is there, you put there. Okay, so it will put one there. Okay, then Mel show. Cool. It will look something like this. Okay. Now this is something we will be feeding into the model, and then the model will be learning to classify. Okay, so our dataset class is done. Okay, then let's look at our model. Okay, so for modeling I'll be using TIM. So this is something similar to what we have in Keras models. So TIM is an open source library. So it consists of all the SOTA models produced during different competitions. So this is a pretty cool library. You just give the name of, you simply give the name of your model that you want, and it will automatically load that. Why is it not loading? Okay, I think this is not the one. It's not the correct repo. Yeah, okay. That's, yeah. This is pretty similar to what we have in Keras models API. Okay, but it is something more PyTorchy, and this is Keras. So yeah, here we have different models. Keras model list. Yeah, in Keras you simply like give the name and you directly load it, and similar to what we have in Team also. So in Team you just directly give the model, create model, and it will load the model that you want. It will basically download the weights and everything. So I'll be using this. Okay. Uh, okay, just run. Okay, cool. Okay, we have gone through a lot. Cool. Now let's create our model class. So model and then standard code. uh, I will not be I will only give the model name so that I can spawn different instances. Okay, so it's called, okay, now let's call the base model. um, so Tim create model. Okay, so I will be giving the model name. Okay, so mainly we will be using an efficient net model. Okay, and we'll be using B0 of it because it's lightweight, it doesn't take a lot of time. So yeah, we're using that. Now the cool thing about Tim is you can pre-configure it. So here I can directly say how many number of classes I have. Okay, it will remove the last layer of the actual model and will just add up this new layer. Okay, so efficient net that we are gonna train, it's basically trained on thousands of classes. It's basically trained on those ImageNet dataset. What we want to train a model on 206 classes. So I can directly pass on that number. It will just remove the last layer and add a new layer. Okay. Now I don't want to use the ImageNet weights, so I will keep it false. Now we also have the option to tell which kind of image we are dealing with. Is it like a RGB image? Because if it is a RGB image, then it has 3 channels. But in our case, we are dealing with a 1 channel image. Okay, the spectrograms. So I can directly give one. So it will automatically change the input layer for the network. Okay, cool. Now let's write the forward method. So it will take a X and it will return self base model of X. Cool. So this is our model definition. Now let's check uh, everything is working fine or not. So another cool thing about efficient net is, so I didn't provide any input layer shape, right? So this will automatically take care of the input dimension. So right now my input dimension will be 128 640. So I don't need to provide that. It will automatically take care of that. Cool. So let's check our dataset class and model class. Okay. So let's create a temporary dataset. So bird clef dataset data dear. Let's sample the first 10 sample 10 rows, and once we have sampled this, we have to reset the index, otherwise uh, the log function will complain. Then model. Okay, and I need to give efficient net, and okay, I just need the proper keyword. Yeah, Kaggle also promotes Tim. This is cool. Okay, this is the name. TF efficient net B0. Efficient net B0. Okay, cool. Now let's call this. So I have the data set. So let's test for 10 spectrograms. Okay, and I will not be training it. I'll simply do a quick inference. So model torch, let's convert our X to tensor. Now it's a single spectrogram. We have to, so when we are passing into a model, we have to give it in a batch form. So a list of X. Okay, that's like the batch dimension. I'm converting into a tensor, and I'm collecting the preds. Then preds torch. Let's call it argmax. So this will give me some y values now to convert them into probabilities. So I will be using softmax and with a dimension of 1. Whichever one is max, just get that and item. Okay. Now this is just for quick inference, whether to check whether everything is working fine or not. Okay. We haven't started training. 640 and -1. And for each spectrogram, let's look at the ground truth and what the model predicted. Ref mapper. What was the name? Okay, ref mapper. Okay, so this will take y. So this will be an integer value here, not the actual string, because here we were converting into integer value. So yeah, that's why here I will be needing the reverse mapper. Then let's look at just to check the image shape consistency. Okay, model pred rev mapper or whatever my model predicted. Okay, this will show. Okay, now once I'm done, I don't want the RAM to be filled, so I will just clear this two thing. Cool. Let's check this. Yeah, so the model is not yet trained and it just predicted this thing, and I see none of them are correct. Okay. Yeah, these are just some random initialization. Now let's write our training code. Okay, training. Okay, so here the competition metric is ROC, so area under the curve, but they are doing some macro averaging over that. So it's better to use their function directly, so we can directly use this function. There's a couple of things we need to make sure, guys. We have this thing as a package to ourselves. Now in order to get that, we can get this from here. Just add this. Okay, so these are some Kaggle metric packages which we can use so that we don't have to bother about all the competition matrices. So it will automatically take care of that. Okay, so we have added the data set. Okay, now few things we need to make sure is we are importing this thing. Utilities. Where is that? Yeah. Okay. Then actually, okay, I could have simply copied that. Okay. Cool. We got this. Cool. Let's import it again. So since I imported a new data set, it just automatically restarted. And I can use this thing now. Let's call thing again. Okay. Now here, this will be my scoring function to get the metric after every epoch. Okay, so that I don't need to implement this ROC UC. So yeah, this function will automatically take care of that. I just need to give proper formatting. Cool. Okay, it's still loading. These are actually good. See, like stunning fire flames. Yeah. Nothing here, but when we convert it to log scale, we got something. Now when we convert it to mil scale, we got something more, which is nice. Okay, cool. Good. Now let's write our training loop. Okay. Now before that, so let's call this thing. So it expects a data frame. Like it expects two things in data frame in order to compute the competition metric. So we will give that to this function. So this will act as a orchestrator for calling this function. Okay, because while training we will be getting raw inputs in form of list and everything. So this function will take care of converting to data frame and feeding it to this score, and then we will just uh, like backtrack, get the score from here and return it from there. Okay. So I'll be collecting list of one hot encoded labels. Okay, similarly I will be doing the same thing for uh, predictions. Okay, then I need to convert the labels to a data frame. So now my labels will be in 0 1 form. Okay, uh, but those will be in floating values. So I can write this condition and this will convert all the zeros to integer values and all the ones to integer ones. Okay, so this is just a condition. So wherever my label value is above 0.5, okay, so it's something like my labels will appear something like this 0.0 because I'm doing one hot encoding, so it will appear something like this. So wherever there is class, it will appear 1.0, and wherever there is no class, it will just appear 0.0.0. Okay, now when I'm applying this filter here, it will convert this to 0. This is also 0 because these are like lesser than 0.5. This is, and this will convert this to 1, and rest everything, rest every 0.0 to 0. Okay, cool. So I don't need that. Okay, now it needs the labels. So I already have a label mapper. I'll use the keys of it. Okay, then I need a preddf. Now in preddf, I will already have the values, and ROC expects probability score, so I don't need to give anything. Okay, this is there. Now I will convert this here and be arrange. Okay, len of labels df, then pred df of id. It just expects a id for each value, for example here. So we are just mimicking that. Okay. Okay, I will call the score function as a callback. Okay, cool. Everything look good. Now let's define our training configs. Okay, first of all, I need some epochs. Now just to test everything is working fine, let's stick to one epoch only. Okay, then I'll be applying stratified k-fold. Okay, so that my train and validation data set will have all the representation for every class, so that I will not be missing out a particular class in between them. So I'll be using 35k fold, and to do that I will be mentioning the number of folds I want. Let's keep it 3. Okay, then device, I'll be using CUDA if CUDA is available, else I'll be using CPU. Okay, and target call, it's primary label. In order to just check this, let's call it like this. Okay, so this will be my complete data. Okay, then I need the stratification. Stratified gatefold. Now it takes number of splits, that's basically number of folds. Whoa. Okay, then I can shuffle it. Okay. Then df fold -1. Okay, now for fold, in my train idx, my val idx, in enumerate of my df, yeah, it has to split first. Okay, y will be df dot target call. Okay, now df dot log wherever my valid index is. I'll mention that as mine. That's cool. I can put this selection num split. Oh, I guess and splits. Okay, cool. Okay, cool. Now my data frame will look something like this. I got the split here. Okay, now let's write the code for multifold training. For fold in range of number of folds I have given. Okay, so I'll get the train df. So df of k fold, wherever my fold is not equal to that, I will consider all those rows as my train data set. Okay, but for validation I will do the opposite. Okay, then train ds will be my BirdClef data set. I'll be in train df, and we'll be using mode equal to train for both of them because we need the labels. Okay, now I'll be writing train loader. Data loader. Okay, train ds. So since the images are pretty small, let's give a batch size of 8. Shuffle through num workers, let's call 2. So just use 2 cores, and if the number of data set there, the length of the data set that I have and the batch size that I'm giving. So if the length of the data set is not divisible by batch size, so whatever is left I can just ignore that, but I will not do that for my validation. Okay. Yeah, I also need TQDM. I need to see my progress. Okay, so the val loader, this will be valds, and since we will not be doing any back propagation here, I'll simply so no gradient calculation will be doing in validation. So I can increase the batch size to 16. So this will like speed up things, and I don't want shuffle to be here, and drop last. Nope, I don't want that. Okay, cool. Now I got my data set ready. So initializing model. Now this is for only one fold I'm doing. Okay. So model I have. I also need VC, so that after every uh, fold training, uh, I can remove the cache. Okay. Otherwise, my memory will just fill up. I can use the same name here. Should not. Okay. Cool. Now I have to provide a device here. Device, yeah, device I already got. Okay, device. So if GPU is available, load the model to the GPU. Then I need to mention my loss function, which we call criterion, and I'll be using cross entropy. Okay, then I will be using Adam optimizer dot all parameters. Yeah, 20 minus 3, let's say minus 4. So let's make it LR, and we'll come back to that. Okay, cool. So optimize is set. Now uh let's store our best AUC so far to this. Okay, so this will help me to save the model weights. Okay, which one to save? Okay, I will just try to save the weights which have a highest best AUC. Okay. Now for epoch in range epochs. So for training, I'll set the model mode to train. Okay, now I need to collect the prediction during the epoch. This running loss 0.0. Cool. Now let's load our batches XY in TQDM. Let's give a description of the training is happening. Cool. Now I need to load my X and Y to my device. To device Y device. Okay, cool. Now this thing has been loaded. Now for the AUC, I need to convert them into one-hot encoding. Okay. Now in order to do that, I need to apply the torch function. So converting to one-hot encoding. Okay. So Y one-hot equal to torch. I remember the torch function. NN functional. Oh, I already have NN. functional. Okay, so I give y here. Now takes number of classes, and I know number of classes. Okay, and then I will convert it to float. Okay, now I will initialize my optimizer. Okay, then model will give me some outputs. Okay, I will compute the loss. Now this is all I'm doing for training and for one epoch, and that for a one fold. Outputs y. Okay, cool. Then uh, let's backpropagate. Okay, optimizer, and let's tune the model weights and running loss, and at the end of the epoch I will be averaging it out. Okay, now I need the probs. A model will give me some floating point values. I need to convert them into proper probability values, so I'll be using softmax. Outputs 1. Okay, train. Now this will be attached to, like, this will be loaded in GPU. So I need to first detach them from the GPU and load them into CPU, and also convert them into numpy arrays. I'll do this is for prediction. I will do the same thing for my y, and that will be my label train. Okay. Yeah. So one hot attach. Okay, cool. So this is for my training loop. I will do something similar for my validation. So for validation, I just need this part. So let's copy this, and yeah, so let's call it's a validation. Now I will change the mode of model to eval. Now this Control Shift D, val loader, and where else I need. Yep, let's convert it into val. So this is now val loader. I'm converting to again one hot encoding, and here I don't need that. And also I need to mention I don't need to calculate any gradients here, right? Okay, and here I will be attaching this. Now this running val loss. Okay, and this will change it to validation. Okay, so loading into device, then one hot encoding it, and I don't need to compute this thing. Okay, so my model will be outputting, then I will be computing the loss function. So I don't need to perform any back propagation. Don't need to do this. Now my val loss is here. I'm summing them up. My probs is here. My val pred. Okay, some spelling mistake. Pred val. Okay, cool. So validation done. All this done. Now I'll be computing the AUC accuracy for my training. Computing AUC and loss. I remember cal score, right? Yeah, calculate score. So here I'll be giving train. I'll be giving red train. Now these are like list of one hot encoded values. So that's why I'm using this concat function. So this will contain a list of batch of one hot encoded values. Okay. So I'll simply concat them with respect to access 0. So this is like they take default values as 0, so I don't need to give that. So yeah, once I concat them, then I'll be getting list of unhot encoded values. Now then I will be giving it to the competition scorer, and we'll get back the uh, AUC score. This I'll do for my training as well as my validation. Label val, spread val. Okay, now average train loss will be my running loss upon len of train loader, and my average val loss will be my running loss upon my validation length of my validation loader. Okay, cool. Now let's print them. Epoch. So after this many epoch, I could have printed this, but okay, let's call it fold. Okay, fold. So this fold, then after this fold, what's the loss acquired? Okay, now let's round the values to 4 decimal places. Okay, then val loss, again average, where's average train loss to 0.4f. Okay, okay, so these are my per fold, what's the loss I achieve after training, and what's the validation loss I achieve after training. Then similarly I will do it for train AOC and val AOC. So AOC train, AOC val. Okay, now to save the model weights, I simply do if best AOC is less than AOC val, I'll simply save the model weights. Now it's better to wait for, so I can do something. So epoch, yeah. So after every epoch I'm doing this. Okay, I'll be taking this here. Yeah, this was something I was missing. Yeah, okay, cool. Cancel. Okay, so after every epoch I'll be doing the validation. Okay, cool, this aligns. Now after every epoch I'll be calculate that. Okay, let's copy this. So epoch, and this is epoch. Yeah, I'll be computing the loss. Okay, and after this, if I got a AOC which is better than my stored AOC, but my best AOC, I will save the model weights. Now I'm using torch save model state dict. Okay, now let's store the fold. fold epoch. Okay, I'm training efficient B0. Okay, then so far the val AUC is val AUC AUC val. Okay, now my loss also val loss, val average val loss, average val loss, and let's store it in here. Okay, okay. Now when I'm done with one fold training, okay, just in the same line, yeah, okay, then I will have to clear this. Okay, so I'll be clearing this so as to like uh, reduce the memory usage. So I'll be cleaning all this. Okay, cool. These are deleted. Then I will be collecting, I'll be calling the garbage collector to remove any cache values, and also I'll call this equalizer. Cool. Nice. So let's do this. Yeah, let's make these imports here so as to maintain a clean code. Okay, and then let's launch the GPU. P100, yes, P100. Cool. I'll just check on the training loop once again. So yeah, this is my train DF. This is my train dataset, val dataset. I'm loading using train loader. Here's my data loader. Okay, here's my model. I'm loading it to device. Here is my criterion. Here's my optimizer. And then I'm setting it to models. And for every epoch box, okay. And for every epoch, setting this. Then I'm giving the train data set, loading them to devices, one not encoding them, zero grad, modeling, calculating the loss function, computing the back gradients, then calling the optimizer, then running the loss function, yeah, adding it to the loss function, then this will get averaged, calculating the probabilities, appending to the pre-train, label train. Cool. Now this will loop over all the data set in training. Then during validation, setting the model to eval, then computing pred val, label val. Okay, and val loader again doing the same thing but not doing the optimizer step, and the back propagation. Cool. I have this and this. Okay, if more than equal to 5, but now I'm just testing. I don't need this. I can remove that, and I will run this. So run all. Okay, okay, it's almost 2 hours. Okay, when did this happen? Okay, now, okay, cool. Now let's run all. Okay. This will take a while. I loaded all spectrograms. Now you guys can see how reproducibility is happening. So everywhere I have given sample, but just because I have set the seed to 42, it's just reproducing the results again and again, even if I'm doing a restart of the whole kernel. So yeah, cool. Uh, Label mapper, this model should be this. Okay, so mate, model name. Oh yeah. So model name. Module object is not callable. Mm. Oh, I'm not calling the one hot encode. Where's that? Where's that? Yeah, so I need to call this right dot. Cool. It started training. So I'm just experimenting like whether everything is working fine or not. So 83. Pretty small. Boom. Okay. Labels. Okay. Got it. Got it. Got it. Somewhere here, right? I can make it labels. Okay. Let's run it again. Wait, labels TF. Okay. It's this. Okay, cool. Now let's run this again. Okay, cool. Let's rerun this. Okay. Um, hmm. Okay. Okay, this is correct. Correct. Here, then reddf. Okay, cool, nice. Let's look at how our label pane is looking. Okay, so look at the shape. So yeah, uh, 83 times it ran. So we collected 83 of them, and we have 8 batches of them, and they are like 1 hot encoded, so 206 per class. So also let's take a look at Pretren. Okay, I'm also appending it to a list, and Pretren of 0 dot shape looks something like this. Okay, so same dimension. Okay, now what I'm doing is I'm basically concatenating all of them. Okay, and I'm giving and I'm generating a 83 times 8 206 uh, dimension consisting of all 206 uh, one hot encoded values. Okay, so when I do np concatenate of red train, okay, so this will give me something like this. Okay, now all the classes, like all the rows that I have, okay, and they are one hot encoded values. Now this is something ROC expects, so that's why I'm giving it like that. Okay, now I think I have exited this. Run this again, and fingers crossed this will work. I want to look at the AOC score. Okay, finally it worked. So it's since epochs, so I have given only one epoch, so it ran like that. Okay, so number of folds 3, so it will run 3 times, and it will run 3 times every epoch, one time. I will see this, and it should be saving my model weights. Yeah, and it's saving my model weights. Cool. So for the first fold, AOC is not that good, and yeah, it's just for like one epoch, so who knows. uh Now I will run this notebook in the background, and I will give around 20 epochs, and yeah, I'll just run this thing again, but now I will be running this with 20 epochs. Okay, and I will remove this line. I will use the complete data set. Okay, cool. Now this will take a while, but this will be the general framework. Okay, I'll just save this training full 20 epochs fnet b0, and let's put fold 3. Set this. Now this will run as a job, and I'm hoping this will finish up in 1 or 2 hours. And yeah, so let's just backtrack. So in our feature generation, what we are doing is we are getting the audio signal. Yeah, we are collecting the audio signal. We are first scaling it up. we are fixating our chunk duration, which is 10 second. Now within that 10 second, how much of data points we want to look, that's basically mean length. Now if I have a data which is where the number of data points is already lesser than my mean length, I'm basically concatenating the same data again and again, and like up to this count times. It's basically a serial division we have to do. Then in my min length, if I have leftovers, okay, if the length of the data is not divisible of min length, okay, this is kind of optional, you guys can say, but this, so right now I have just taken the first value, okay, for like the first min length segment. If I am doing some uh, like what can I say? So if I'm stacking them in a grid, then it will help. So by stacking, what do I mean is, so so let's consider this one. Okay, this is my audio signal. Okay, so if I'm considering three at a time, okay, then this will help me. Okay, how I can stack this audio signal for 10 second each. Okay, then I can give it to the Mel spectrogram. Okay, and it will it will again do the same thing. Okay, now just for the ease and the convenience, I just took the first length value and I just created a new dimension. Okay, instead of this, I could have stacked 10 seconds audio signal upon each other, and then I could have trained it. So yeah, once you have your desired data points, convert them into Mel spectrogram, convert it to a decibel scale, and just normalize it because you are giving it to the model. Then yeah, just fix it with the number of features you want from the Mel spectrogram. Okay. And once you have that, this will be ready. It will look something like this. Then you have your model. Tim provides base classes for all the models. And yeah, just do that. Then just the for testing. And yeah, these are just some configs which I'm doing for training. This will take a while. I can look at it. Hmm. It's I think it probably running those plotting cells. That's why it's taking time, and also that sampling of audio signals. That's why. Cool then. I hope you guys learned something new. So quickly, I will be uploading the inference notebook also once my model gets trained. And yeah, if you want some guidelines, you can watch that video. Uh, Comment if you have any doubts regarding the code cell that I have mentioned here. So yeah, thank you for watching, guys. Bye.